Swayam Prabha. Digital India. Educated India.
Good morning. With this lecture number 33, we are starting a new module, module 6, which deals with the matrix analysis of plane and space frames. If you recall, we have already covered 5 modules, and actually you are now in a good position to quickly understand more complex structures like plane and space frames. The methodology is the same. And we have one last module left which we will take up. It is second order analysis and study of elastic instability of beams and frames. So, the space frame element is the most generic, most complex element that you can get in matrix analysis. It is a very powerful element. As you can see, you have 6 degrees of freedom at each end of the element. So, you have 12 degrees of freedom, which takes care of bending about 2 orthogonal planes, vertical plane, horizontal plane, which takes care of torsion and which also takes care of axial force. If there is a variation in bending moment at the 2 ends, you have a shear force coming into play, and so the shear force can be in both vertical and horizontal planes. All other elements that we have studied are actually special cases of this one element. If you take the stiffness matrix for a space frame element 12 by 12, if you delete rows and columns respectively, you can downgrade it to a plane frame element, to a grid element, to a beam element, to a space truss element, to a plane truss element, and to an 1D axial element. So, they are all special cases of this element, and as usual we will learn to apply the conventional stiffness method, the reduced stiffness method, and the flexibility method for plane frames, and for space frames we will just demonstrate the application of reduced stiffness method, because it takes a lot of space and time to do a big frame. So, right now we will be looking at the application of conventional stiffness method to plane frames using the plane frame element. As you can see, there are 6 degrees of freedom, 3 at each end. You have an axial degree of freedom which you get from the truss element, the axial element, and you have the beam element with bending about the vertical axis as shown here, and shear force. Is it clear? So, it is quite easy. You just have to put together the stiffness matrix that you derived for the axial element along with the beam element, and we conveniently assume that there is no interaction between the two, and you get the stiffness matrix for the plane frame element. This is covered in the chapter, actually it is chapter number 6 in the book on advanced structural analysis, and we begin with the conventional stiffness method. So, I have tried to show the same map in all the lectures that we have done to show that we are basically following a very systematic way of solving problems. The conventional stiffness method is the method that is used in software programs that you buy commercially, which is used extensively in actual structural analysis. Reduced element stiffness method is very good if you want to program yourself, and some of your senior students have developed beautiful programs using MATLAB which actually can do space frame analysis, and I like to demonstrate this at some point just using matrix methods. Reduced element stiffness method can also be used, and there is also the flexibility method, which on a case to case basis you could use, because it's appropriate to use the flexibility method when the degree of static indeterminacy is very small, in relation to the degree of kinematic indeterminacy. So I am just playing back to you some slides that we have already seen. You remember we began with a plane truss element which had a 4 by 4 stiffness matrix, 4 degrees of freedom. It is very easy to remember the stiffness matrix, 2 rows and columns will be in zeros, and the others are simply Ea by L and minus Ea by L. So this is familiar to you. In this truss element you will find that the 0 rows and columns correspond to the shear force. If you use it in a plane frame element, you have ability to take shear, so they are no longer going to be zeros. That is a big difference. Then we looked at the plane truss transformation matrix. You remember we use this cos theta sin theta transformation. We need to invoke the same transformation when we do a plane frame element. We next looked at the beam element. In the beam element you had bending moment, shear force at two ends, you had 4 degrees of freedom, and we use this element not only for the beams, we also use it for the grids. So we are familiar with this, and we learned to generate the stiffness matrix using different alternative approaches, including the conventional displacement approach where you assume a displacement function using geometry, and then you work with that and generate the stiffness matrix. We also looked at the transformation matrix for a beam element. We found that the TI matrix is an identity matrix because conveniently the local axis can be made to align with the global axis, so x is x star, which you can't do in a frame. In a frame the element can be oriented in any direction. So now with that background it is quite easy actually to put things together and straight away derive the stiffness matrix for a plane frame element. Will you try it out? Write down the 6 by 6 stiffness matrix for a plane frame element with the coordinates as shown here. We number these coordinates 1 star, 2 star, 3 star to align with the x, y and z axes. 1 star refers to an axial degree of freedom, 2 star is a translation, a deflection which is normal to the longitudinal axis. The corresponding force is a shear force. 3 star is a rotation in the xy plane, which means with respect to the z axis, and we follow the same directions and numbering sequence for the end node. So you have 1, 2, 3 at the start node, 4, 5, 6 at the end node. Just write down the stiffness matrix assuming that there is no interaction between the axial degree of freedom and the flexural stiffness. Okay, no interaction between axial stiffness and flexural stiffness, and if you do that you will find that you just have to add one additional row, or rather 2 additional rows and columns corresponding to 1 star and 3 star to your traditional beam element stiffness matrix. You remember we did something similar for the grid element. In the grid element we added Gj by L, here you add Ea by L. There is also one notable difference. In the grid element which we discussed yesterday, 1 star and 2 star referred to the flexural degrees of freedom and 3 star was the torsional degree of freedom. Here 1 star corresponds to the axial degree of freedom, so it comes on top. You can, instead of writing Ea by L, if you take out Ei by L outside the brackets, then you would say A by I. Incidentally, A by I is also 1 by r squared, where r is the radius of gyration. So it is the only additional terms you have is that Ea by L plus and minus, which is easy to add. So it's not at all difficult once you're familiar with whatever we've done till now. Is it clear? So you will find that the plane frame element is essentially a combination of the truss element and the beam element. Now, do you think there is some possible interaction between the axial and flexural stiffness components? Are they really independent as assumed here? We will study this in the next module, in module 7, where you realize that there is an interaction. There is an interaction between the axial degree and the flexural degree, and in fact if the axial force is compression, it can be quite significant. If the compressive force is high, you have a phenomenon called buckling that is possible. If the axial force is close to the critical buckling load, the flexural stiffness degrades to what? To 0. That is why in when buckling takes place, there is no flexural stiffness left in the beam. So which in turn suggests that axial compression can actually reduce your flexural stiffness, and conversely axial tension can enhance your flexural stiffness. But these are second order considerations, they do not come in the realm of first order structural analysis. So in this module we are doing first order structural analysis, we do not look at what are called P delta effects, and we conveniently assume that these two stiffness components are uncoupled, that they are not, there is no interaction between them. Is it clear? Okay. And this is reasonably true if you are dealing with well proportioned members which are not slender and your axial forces are not very high, not close to your critical buckling load. The other interesting thing to notice, the rank of this matrix is not full. What is the rank of this matrix? 3, because it's the element itself is physically unstable. To hold it in place you need to arrest 3 degrees of freedom, and we will do that when we do the reduced stiffness method. That is why this matrix is singular, it cannot be inverted. There is no flexibility matrix possible by inverting this 6 by 6 matrix. You have to reduce it to a 3 by 3 matrix, which we will do in the reduced element stiffness method, and the inverse of that is the flexibility matrix. As far as the coordinate transformation is concerned, I am showing a picture which I showed in module 3, where we tried to show the relationship between the degrees of freedom expressed along the global axes with respect to those expressed along the local axes, and that transformation is Ti, and if you take one of those ends you will find that it forms this familiar transformation, the rotation matrix, where you have cos theta minus sin theta cos theta sin theta, and you have 1 corresponding to the 3rd degree of freedom, because there is no need to do any transformation with respect to the z axis, because we are talking of rotation about the z axis. So I hope you are familiar with this, and knowing this you can easily write down your transformation matrices at the two ends, put it together, and you have this symmetric Ti matrix where each of those blocks in the main diagonals are familiar to you. Is it clear? So we have to use this. Yes, any doubt? So it is familiar to you, and so Ti matrix is no problem, and the beauty about this matrix is the inverse of this matrix is the transpose, because it is an orthogonal matrix. Okay, so you also need to indicate the local the global coordinates in parenthesis as we did earlier. This is familiar to you, this is a path we will take to do transformations. You will find that if you are programming, it might be beneficial to do it in a systematic manner. For example, if you, for each element, if you pull out the direction cosines in terms of theta I, and you call them Ci and Si, and if you know the length of the element, you can generate some properties straight away. So this is a typical transformation matrix for any element in your plane frame, and once you input the properties, once you write the coordinates, it can generate this automatically for all the elements. It is important to note that you must also put the linking coordinates, which I have shown here, LMN, PQR, and it is very easy to assemble the stiffness matrix. From the properties, you can write an algorithm like this in terms of alpha, beta, zeta and delta, and you can, if you want to program it, it will do the stiffness matrix generation for at the element level also effortlessly. You can go one step further and do this product multiplication also. You can feed in these coefficients, these elements of your Ki Ti matrix, because this is necessary for you to get the internal forces. You can go one step further and pre-multiply this matrix with Ti transpose, and you can feed in this in terms of the geometric and material constants that we had expressed earlier. So if you are interested in programming, you can directly feed in these values, but you can also allow each multiplication to be done separately. The choice is yours. We have also looked at equivalent joint loads. Now when we did trusses, the equivalent joint loads came not from nodal loads, not from distributed loads, but from lack of fit and temperature effects, right. When we did the 1D axial element, you also had the possibility of intermediate loads. When we did the beam element, we did not have temperature loads, but we had intermediate loads. We also had support settlements, which you also had in the truss. Now in the frame you can have anything, you can have a mixture of everything, you can even have temperature effects. So we will take a look at the large variety of problems that you can get. Okay, so you have to follow the same procedure. You have to find the fixed end force vectors, you have to include any additional fixed end force vectors that you get from initial displacements. You have to do this transformation to slot your fixed end forces along the global coordinates, and you have to work out the equivalent joint load vector. Procedure is same, the map is same, the territory is familiar. We will do two problems. I hope we have time to do two problems, or at least one problem exhaustively in this session. So take a look at this truss, this plane frame. It's got all the familiar complications. You have an intermediate load there, 100 kilonewton. You have a nodal load there, lateral load of 50 kilonewton. We've also thrown in a support settlement of 10 millimeter, right. The E value is given, I value is not directly given, it's given in terms of the cross sections. So 300 by 300, the two columns are square, and the beam has a depth of 450 mm and a width of 300 mm. It's a typical single bay portal frame, and let's learn how to analyze this. We should know what the displacements are, at least at the joints, the maximum displacements. But more important, we must know the support reactions, we must know the bending moment diagram, the shear force diagram, the axial force diagram, which is all easy once you have the free bodies. Okay, so how do we proceed? Well, again this procedure is very familiar to us. We are following exactly the same steps. First the coordinate transformations, fixed end force vectors, equivalent joint loads. Next the element and structure stiffness matrices. Next we write down the equilibrium equations, and in this case the support settlements are there, so you have to bring in that into solving those two equations. You solve the first equation, you find the unknown displacement at the active coordinates, you plug in those values in the second equation, you get the support reactions, and finally what is the last step? Member forces, there you are. So it is very familiar, and the member forces are nothing but your equivalent slope deflection equations. You have the fixed end forces and you have the additional end forces that you get from the joint displacements. Okay, so I hope now you are comfortable dealing with any problem because the procedure is well laid out. You just have to do your transformations properly. You will find the conventional stiffness method is actually very straightforward, not much thinking to do. It is a reduced stiffness method which can be tricky because you are taking shortcuts in reducing your degree of kinematic indeterminacy. Personally, I think that is a real challenge if you want to do things manually and write your own programs. Flexibility method similarly is very challenging, but conventional stiffness method, except when you have local complications like internal hinges, are very straightforward, systematic, you can't go wrong. So let us demonstrate this. So first we have to identify the coordinates, the global coordinates. As usual, we will start numbering from the active degrees of freedom. Since the ends A and D are fixed, only B and C have the active degrees of freedom. We do, since we chose the origin at A with X pointing towards the right and Y pointing towards the upper region, we follow the same sign convention, 1, 2, 3 at joint B and 4, 5, 6 at joint C. Those are the green colored arrows are active degrees of freedom. We also have restrained degrees of freedom, and they are 7, 8, 9, 10, 11, 12 following the same sequence, and once we know those, we know the support reaction and so on. What is the input data given to you? Do you have any nodal forces? Yes. So you will find that F1 is plus 50 and D11 is minus 0.010 meters. So you must, rest are all zeros, clear? You also need local coordinates. So instead of writing 3 separate figures, we can write one common figure for all, and this is a standard picture which we will show in all plane frame elements. In this particular problem, that angle theta with respect to the global x axis is either 0 degrees for element 2 or 90 degrees for elements 1 and 3, but in general it will look like this: 6 degrees of freedom, and this is the standard TI matrix, the transformation matrix, where you shift from global axes to local axes. Okay, so it's easy to generate this if you make a table, which is what I suggest you do whenever you deal with any frame. We've shown a single story single bay frame, you can have a 100-story 20 bay frame, it makes no difference. Okay, you have to systematically follow this procedure. You have to identify your elements, you have to identify the start nodes and the end nodes, you have to write the coordinates of those start and end nodes, which is what we did when we did the plane truss. The plane frame is similar, and you need not explicitly calculate those theta values. You do not need the theta values, you need the directions, cosines, cos theta and sin theta, which is very easy to generate from the coordinates. Even the length comes from the coordinate, you know, we have done this before, so I'll go ahead. You can also in this table put in your EI values and your EA values, EA by L and so on, all that you need to generate your TI matrix and your stiffness matrix. So the moment you give in the input, you can also, if you are writing a program, ask it to generate a visual picture of the structure, so that you can verify at one glance whether you missed out some element or whether some element is mislocated, which you can do when you do your programming. In fact, all software programs do that. They also have a facility where you do not do all this table business, you actually sketch a picture and it will generate this table on its own. So those are all tricks that you can carry out, and we are not studying those tricks here, we are just studying how this black box works, what is the algorithm inside it, and can we do a minimal amount of programming and be able to make the computer do structural analysis for us. It is a systematic method, It follows certain laws and it is easy to understand at this stage. So it is very easy. With that table you can generate the TI matrices for the 3 elements T1, T2, T3, where theta is 0, cos theta is 1, where theta is 90 degrees, cos theta is 0 and sin theta. So these are very straightforward, very easy to generate. If you look at the element 2, T2, it is like a conventional beam element, and that is why it looks like it is an identity matrix, right, it is like a beam element. The columns are frame elements. The linking coordinates are very clear. For the second element it is clean 1, 2, 3, 4, 5, 6 because they are all active degrees of freedom. For the first element it begins with 7, 8, 9 and then 1, 2, 3, and for the third element it is 10, 11, 12. We are starting, the start node is at D, okay, not at C in this particular case. You can choose your own sign convention. 10, 11, 12, 4, 5, 6. Is it clear? Remember, when you do a large frame, it is better to follow those suggestions we gave in the third module of reducing your bandwidth by numbering it along the shorter direction. But we are not looking into those aspects at this stage because we are dealing with very small frames. It does not really matter when you are dealing with a small frame. Okay, next job. Is this clear? You can do this easily and you can program it if you wish. Next job is to find the fixed end forces. So what are the fixed end forces? Well, you have, it is easy to generate, it is a beam element. You have, of the 3 elements, only element 2 will have fixed end forces because elements 1 and 2 have no lateral loads on them. So you have a concentrated load located 2 meters from the left end. You know the formula WA AB squared by L squared. Put the signs correctly and work out your vertical reactions. You do not need to draw the shear force and bending moment diagram, but if you wish to you could do that. So okay, have you all understood? You can pull out the fixed end force vector for that second element, and for the first and third elements it is going to be null vectors. Clear? Nothing new. This is what we have been doing for the beam and the truss and the axial element. Clear? So you have got this. What is the next step? You have to switch from local to global. How do you do that? You just have to pre-multiply with the transpose of the corresponding TI matrix and you put alongside the linking coordinates. So you know the linking coordinates, so you first do that product, and after you have done that you have to do the slotting. That means whatever you get in coordinate 1 from the 3 products you add up algebraically. Is it clear? And after you get the answers you can just go back and check and see if it makes sense, because visually you can inspect and see whether it makes sense. And you will find that in this case, because only the top beam, the horizontal element has loads, nothing is happening at your FFR level. There is no fixed end force going to your restraint coordinates. Okay, makes sense. You can also draw a sketch after you find the net load vector. Net load vector is FA minus FFA. FA has only one nodal load, F1 equal to plus 50 kilonewton. So you do this product and draw a sketch. You actually converted your original problem to this problem, okay, and the equivalence is they all have the same dA vector, the active displacement vector, and you also note that in addition to the forces you have support settlements which comes from the dr vector. You have D11 having a value of minus 0.01 meters. Next you generate the element and structure stiffness matrices. Actually you can do this earlier because the computer does not wait for the loads, it straight away does all this. These are properties of the structure. you can write this algorithm. We've already plugged in those values in the table, so it can generate in a jiffy, it will generate all this, right. There is nothing much in it. Once you have done this, your next job is a little tricky. What do you need to do now? You have to assemble all these matrices by first converting them from local coordinates to the global axes and then slot it, and that takes a little thinking. So by summing up the contribution of Ti transpose Ki star Ti, you get Ki. Ki is the same stiffness matrix realigned along the global x, y and z axis, and it will typically have a quadrant format as shown there. You can say it is Ka, Kb, Kc, and Kc transpose on the other side, it is going to be symmetric, right. So I can generate for each element these 3 values Ka, Kb, Kc, and I put a superscript I to identify which element is where, and now I should do my slotting very carefully. So the slotting comes from understanding the linking coordinates, right. So for each of them I have a 6 by 6 matrix, and at the appropriate coordinate locations the structure matrices matrix K of order 12 by 12 satisfying F equal to Kd can be assembled. It takes this form. Now look carefully at that form. 1, 2, 3, coordinates 1, 2, 3 will be affected by which elements? By 1 and 2, okay. Now it is going to be affected by the tail end of 1 and the start end of 2, the tail end of 1 and the start end of 2. That is how you write Kb of 1 plus Ka of 1, Ka of 2. Is it clear? That is a clever way of doing it. Now you can program it to do this automatically, but if you are doing it by inspection you have to do it carefully. So you need to assemble this with some care. And would you like to do an assignment, one problem of this type, so that you get a feel for it? So your last assignment, you will do this by inspection. So it's going to take time if I'm going to explain this by myself, but I would like you to generate it, make sense of this and generate that matrix, and it should be symmetric. So it's easy to generate one side of it. Any doubts? Clear? You can generate this from all those 3 matrices, and so this is the K1A, K1B, K1C, K2A, K2B, K2C, K3A, K3B, K3C, which once you assemble you put all together and you get the full matrix. You get KAA, KAR, KRA transpose and KRR, okay. So you have got the full structure stiffness matrix, but it takes a while. You do not attempt doing this manually, it should be done through MATLAB. Maybe to make your life simpler, in your assignment I will give you a 2 member thing, so you have to add only for 2 members. So let's see how you do that, okay. Next step is very clear. You have got your structure stiffness matrix, you have got the transformations, you have got the net load vector, you have this familiar equilibrium equation, and you plug in those values and you can find the active displacements by solving that equation. You KA8 inverse, the computer can do it for you. You have a MATLAB inversion program which can handle it. Your matrix is well conditioned, so you are pretty well assured of the results that you get. And it is nice at this stage to look at those numbers. Do they make sense? Is that the kind of values that we get? Do not get scared looking at them. Try to draw the deflected shape. It will look like that, okay, and you will find that everything makes sense. D1 tells you that joint B is going to move to the right by 13.394 or 39 39 mm, that is okay, 13 mm is fine for a big structure like this. The right end will move 13.33, the little difference is because of the axial deformation in that member and a bit of rotation. Joint B does not go down at all because there are far too many zeros there in that, right, but you will find that C goes down and that corresponds to D5, goes down by 10.08 mm, which makes sense because your support is going down by 10 mm at D. So this is the kind of feel you should get once you get the output. Do not just get the numbers and say I have got, just give me full marks for what I have done. See what you are doing, understand the physics behind the problem, it should sway the way you expect it to sway. So that is how the displacement vector should be interpreted in practice. Then your next step is to get the support reactions, which you can get by solving that equation, and you plug in those values and see whether it makes sense, see especially whether you are satisfying equilibrium. So that check you can do, you need to do many checks including the moment equilibrium check, but at the very least you can add up the forces in the vertical and horizontal direction, it should all add up to 0. Then you say okay, at least my solution satisfies equilibrium, that is for sure. Hopefully it also satisfies compatibility. It will, because the stiffness method begins with compatibility and equilibrium is the final solution, okay. And then your next step is to find the member forces, which you can do by you already have these computed and stored in your memory, the Ki, Ti, and you plug in those values, you get the member forces, okay, for all the 3 elements. Then you draw the free bodies. When you draw the free bodies, you will find you are now in a position to draw the bending moment diagram, if you wish the shear force diagram, etc., etc. Is it clear? It is as easy as that. So we have done one plane frame element solving by this method. Looks like we finished early, so it is a good time for you to raise some questions, okay. So on whatever we have done till now, do you have any questions? We were able to go fast only because we have travelled quite a distance to reach this stage, right. So we have done the truss element, we have done trusses, we have done beams, we have done grids, and now we are doing frames. Okay, let me ask you a question. Take that same plane frame and let us subject it to temperature loading. Let us just heat it up. How would you solve that problem? Okay, let us say the temperature is increased by, and you can have seasonal variation of temperature of this order. How will you deal with this problem? Sorry, fixed end moments. How do you get fixed end forces? There are no forces given. Sorry? No, let her answer. Yeah.
Define the change in length and the force due to the.
What kind of force will you get? So how do you find the, okay, you find the change in length, you have elements 1, 2, 3. The change in length will be, we use the notation E naught I will be, sorry, Li alpha delta t, right. Okay, you have got this. Now what? This is the free elongation, if it's allowed to freely elongate. Sorry? So you should say that I take the primary structure. In the primary structure, all these ends are restrained artificially. When in the primary structure you have a temperature rise, you end up with axial forces in all those members which you can calculate. Then what? That's what we did in a truss, remember? Added to what? There's no other loading.
That is the vector. That is the fixed
That
net load vector.
is FF star.
Okay, so we are saying you have a delta F vector at the element level, right? Let's do it for element 1. Okay, what will it look like for element 1? This will be, yes, what will be the size of this element?
6 by 6.
It will be 6 by 6, right? So 6 by 1, sorry, 6 by 1. So what do you write? What do you write for the left hand? So this had, if you remember, 10, oh sorry, 7, 8, 9 and 1, 2 and 3, right? So the linking coordinates are 7, 8, 9 and 1, 2, 3, and the element itself had 1 star, 2 star, 3 star, 4 star, 5 star, 6 star. How do you fill up this? What is the first element? So we are looking at an element like this with this as 1 star, this as 2 star, this is 3 star, 4 star, 5 star, 6 star, right? So, and this is the element 1. So this value that you get, what do you do with that? So what should I write?
Multiply A by L.
Is it plus or minus?
Minus.
Well, if you heat this up, it's going into compression. It's going into compression. So what are the end forces that you get? If it goes into compression, yeah, so this will be positive or negative?
Negative.
It's going to be positive. It's going to be positive. It's going to, compression means you press it down like that. So this will be positive and this will be negative. So let's just write, so what would this quantity be? So this will be positive and this will be negative of, let me just write N1F.
That's 8 and 2.
I'm sorry. So let me say plus N 1F minus N1F, where N1F will be K is what? A by L for the first element times E01, right? So you will do that. What do you get here? 0, here 0, here 0, here 0. Likewise, you can generate this vector for all the members, right? In fact, we use a word called delta star initial for this. Okay, you have done that, then what do? You now need to convert this into the global coordinates by pre-multiplying it with T1 transpose, and what do you get? What do you get? This will give you, well, finally if you add up for all the elements, you will end up with delta F FA delta FFR. So you have got nodal forces, you have got equivalent joint forces, and you will find that you are actually going to analyze a structure with what kind of forces? When you have to apply it in the negative direction. What is your net load vector going to look like? What is it going to look like? Okay, show me here. Do you have a force acting down? Yes, right? Will it be acting down or up?
Down.
No, you had compression acting here. You have to reverse it because you kind of had to hold it down. You have to let go. So will it act down or up? It's going to act up. So you have a force acting up here, acting up here. What about here? This wanted to expand, you held it back. So finally, plus you had some support reaction. So you are actually analyzing a structure like this. Is it clear? And will this cause bending? For sure it will, because if this moves laterally, this doesn't move, you have got a chord rotation. So you will have a curvature, you will have a bending moment. It is a very interesting problem, one which I wish you will solve on your own. So the subject is beautiful if you can link your left brain with your right brain, understand the physics of the problem, and you have got a powerful tool to handle any kind of loading on any skeletal structure. Thank you. Yes, I'm glad you raised this point. You are right. We have to correctly put the linking coordinates. As far as the element is concerned, 1 and 4 are always actual degrees of freedom. So you are right. This should find a place here. And this here, because this corresponds to 1 star, this corresponds to 4 star, and this incidentally is F star F. So the mistake we made was in putting the linking coordinates. 1 star actually matches with 8 star, not 7 star, and 2 star matches with 7 star. So that's a correction we need to do. So this will be 8, this will be 7, this will be 2, and this will be 1. So you strictly follow the fixed end forces at the element level and place the linking coordinates which come with your TI matrix. Be careful. Thank you.